All right, everybody, let's get together for Dzmitry's talk. Ex-lead developer of WGPU, and we're super excited to have him join us. They rode here in a fully autonomous drive in an engineering vehicle in Tesla here. So maybe he'll give us some more updates on that.
Hello. I'm glad you guys survived through the first two talks, and I'm happy to kick it off with a talk about WGPU and different ways to talk to GPU in Rust. So if you were wondering how this is done, this is a good overview of all the tools we have. And I've got to warn you ahead of time, these slides were not checked, but hey, for political correctness. They are all NFT protected, so be careful when you take photos. I'm gonna know. Let's go. So this is not who I am. This is what I did in Rust. I do not represent my employer. I do not represent WGPU developers here because I'm no longer developing it. But I have a lot of context to talk about it, nevertheless. So I've been programming in Rust for 12 years, long before 1.0. I started with like times where it has weird symbols, it had a runtime. It was a different language by then. I think 0.4 was the version. And I've been writing a lot of things. Some of them are, like, I contributed a lot to CGMath and later created an abstraction for math libraries, which is called Mint, to unify them all. I created the Rusty object notation format that's used by a lot of projects, including Bevy. I did a lot of threading systems, unsafe code that Daryl likes, with fibers, specs, entity component system, and lately Choir, that's a task orchestration system. And I did contribute to applications, which mainly Firefox, the browser, and Z. In Firefox, I did the WebGPU support and a lot of the graphics stack. And Z browser is powered by basically all of the graphics and portable code for Linux, and some of it is also working for Windows. Most of my work was done on graphics, libraries like GFXRS long ago, and then 3RS, WebRender at Mozilla. Of course, WGPU, projects like Rusty Avengers, and lately Blade, which I'm going to talk more about. So we're going to talk about GPU abstractions and WGPU, and then conclude on Blade. It's the library that I'm working on right now. This is one way to look at them. There are many trade-offs. Some of them are how light your code is, how safe your abstraction is, and how portable you can run it. And some of the things here is like Ash, that's the thing that Zero Matter uses. This is on the right, so it's lightweight abstraction that's not really very portable. On the left there, we see Volcano, which is safe, but also targeting just Vulkan. In the very middle, we have OpenGL abstraction GLRS. And nearby, we have WGPU, of course, which has the safety and portability, but maybe not as lightweight as we would like. And then the other two positions are taken by WGPU HAL and Blade. So WGPU HAL is the layer of WGPU that is powering the abstraction itself, and it's unsafe. It's not what you're using when you're talking to WGPU. It's very light, and it's targeting the platforms that you know WGPU runs on, but it's unsafe. And Blade here as well, it's also unsafe. Okay, no, that's not the right one. This is the island of platforms. At the center, we see Vulkan, the favorite API of many, including Zero Matter, including some of the places I worked at. And it covers a lot of the land for Linux, Android, and Windows. I specifically did not make it cover the Apple platforms because natively it's not supported there. the supporting layer is a user space library. So technically, if you're relying on Molten VK, it's no better than relying on a Rust crate. It's all user space. There's no difference. I would say choose something Rusty better, because at least it's internally better than a Molten VK. And Vulkan is not covering all of the Linux and Windows. There are still hardware that cannot run Vulkan or cannot run the Vulkan that you need. For example, you need Vulkan 1.1, and this hardware that like Intel GPU is not supporting 1.1. So it is useful to also support OpenGL ES, which covers all of those. Oh. This is a safety aspect of the API. We're going to talk about safety. Rust safety is a very complicated topic, and I'm not an expert in it, but as a user of the language, I can say that you expect it to be deterministic, or at least if you have like data races, then you have undefined data within some expectations, right? Some of the API abstractions here, they can sort of guarantee the host side safety, but can do nothing about the shader side safety. And Vulkan itself does not give you any tools for that either. So that's how it may look. On the host side, you can be safe, but then on the shader side, you can do wild things, and it can lead to interesting outcomes. For example, if you're writing data outside of your buffers on GPU, you can say, oh, like, it's GPU, who cares? It's not going to leak into my main computer, which I care about. But then Vulkan has an LLVM pipe implementation, which runs completely on your host. And like whatever you write there is running on your host, and it can be compromised. So shader API safety is also important. We'll start with Glow. That's an OpenGL library that's currently maintained by one of the core developers of WGPU, Joshua Gruss. So I highly recommend it. It targets OpenGL, OpenGL ES, and WebGL. And the safety of this is sort of weird topic, because OpenGL was developed at times where safety was not a concern in general. Like as long as it draws, it's fine. Everybody was using C at the time anyway. And now it's more of a priority for Vulkan to describe what kind of outcomes for your commands are. So it's a weird situation where technically OpenGL is safe, but in practice it's not. And Rust API for Glow is unsafe, which is unfortunate. The overhead of the library itself is zero. It's just straight up OpenGL calls. However, no sane platform wants to support OpenGL natively. This is a dead API. Whatever, if you're NVIDIA, you want a single API to your GPU. You don't want to support like a zoo of APIs, especially old ones like OpenGL. So whatever you run it, there is probably some translation layer involved. And given that, the chances are that it's not going to be much better than whatever you would do in your own userland translation layer if you would target other APIs. It's downloaded every 8 seconds, so a very popular library. Just as I talked about it, was with like 12 downloads or something. We'll go to Hash. That's the library used by Zero Matter. It's completely unsafe. It only supports Vulkan. It has not very good ergonomics, but it's used widely. Download it roughly the same amount of frequency, so every 9 seconds. Very popular choice. And we have Vulcano, which is an attempt to provide safety for Vulkan applications. Library is fairly old. It has a layer of ensuring safety, which works at command recording level, and it has to scan through all of the resources you access on every draw call or dispatch call. So if you are using, say, Vulcano, it's going to be very slow. So I put overhead as ZZZ here. Otherwise, it can do automatic barriers for you. It doesn't provide safety on the GPU side, the Simpsons picture I posted, only on the host side. And it's downloaded every 2.5 minutes. So maybe once since I started talking about it. Also, shader processing is done by C++, which means it's not a pure Rust library. Then we go to the crown jewel of Rust graphics, WGPU, which is completely pure in Rust. So both the host side and the shader translation are pure Rust libraries that you can inspect and run. It is completely safe. Both host and shader side is safe. To provide safety, it goes through a few motions, of course. On the host side, it's one kind of motions. We're going to talk about it more. On the shader side, it has to inject like bound checks, any kind of behavior that Vulkan SPRV does not guarantee. In theory, in WGPU, we have to configure so that there is a guaranteed outcome. Things like, I don't know, overflowing an integer or something. So things that you don't even think about. But if you are using WGPU, I think you should be able to just tell it, like, don't bother, don't make my shaders safe, if you really want to. So it is configurable. In terms of overhead, there is tracking of resources so that it guarantees both the lifetime and the usage of resources. That is correct. And it happens as you record your command buffers. So there is cost to this, and whenever you record a draw command, the API tries very hard to record it in the command buffer immediately. And that's how it worked last time I checked, but it comes with its own costs. It has fairly good ergonomics, simple abstraction, WGSL shaders, and you don't need to worry about resource states or lifetimes. It's all very, very rusty, I would say. It targets the widest amount of different backends. So all of the next-gen backends, D312, Vulkan, Metal, and OpenGL, and of course, WebGPU and WebGL. So anything under the sun practically is covered, other than consoles maybe, but that's going to be like a task for some forks. Download it roughly the same time as Glow and Ash, so every 12 seconds. Very much downloaded. And this is the HAL, so the lower level abstraction that WGPU builds upon. It's completely unsafe, but it's still purely Rust, same backends, directly mapped to the API. So in WGPU HAL, whenever you record some command, it directly just injects this call into the command buffer. There is no overhead at all. It's much nicer to write than Ash. It is simpler. Like the resource state architecture is much simplified comparing to Vulkan. And it's downloaded together with WGPU. There isn't many users that specifically target WGPU HAL, although I think it's a good opportunity for like AI libraries, for example, to target, because it gives you all the support you need and you control your own safety and you know how to make it safe on your level. You don't need WGPU to provide safety for you. Then we go into Blade. That's the library I've been working on lately, also using WGSL shaders, so Naga for shader processing. And it's not safe. I'm not trying to make it safe. I'm going to talk about it more. It targets Vulkan Metal and GLES with WebGL. So comparing to WGPU, it's missing D3D12, Desktop GL, and WebGPU. Those are not current targets. But if you're aiming to run on desktops or mobile phones, it's all there. It's all running natively. It has no overhead for translating the commands because it's also directly mapped. However, there is a caveat about overhead on the GPU side, which I'm going to be talking more. And in terms of ergonomics, I think it beats pretty much everything in this list because you don't need to care about the bind group layouts nearly as much as WGPU. Again, we're going to talk about it more. Also, no resource states, and you still need to do manual resource destruction. That's probably the biggest problem. And it's already downloaded frequently, like every 15 minutes. This is based on crates.io and GitHub statistics. This is another way to represent the same libraries. Between ergonomics and safety, Ash is on the left, It's not safe and not ergonomic at all. And as we go into the territory that's more safe, we meet WGPU Hull and Volcano and Glow, and WGPU is on the opposite corner. It's like most safe and fairly ergonomic. And Blade is unsafe but more ergonomic. So we can now go to the next step, which is talking more about WGPU. What this is, generally, it's an implementation of the API that's developed by browser vendors as well as Intel and other companies. So it's a conglomerate of companies, API called WebGPU. And the idea is we would translate into the native APIs on those platforms that browsers can run on. So D3, D12, Metal, and Vulkan. We would use our own shading language. We would do the synchronization for the user, this part. And very importantly, we would allow user threading. That's something that WebGL doesn't have, OpenGL doesn't have. And this is the feature, the landmark of the next-gen APIs, that they support threading models. So with those ideas, we embarked on the creation of WebGPU. And that I think I mentioned, these are the intersection of the three APIs that we would build our API on. Now the boring part, the history. This was not shown anywhere, so a unique slide. 2016, browser vendors talk with each other on multiple Kronos meetings, and they present projects on WebGL Next. That's their name of the initiative to see what comes after WebGL. And this is where I also come in and I like show something that's Metal-like for the web. Apple shows something similar, and Google shows something entirely different. And throughout 2017, we're trying to converge on something common, like trying to organize the working group together. And by 2018, the working group is set and is collaborating on a Sketch API. This is where we had the GPU web within W3C. It's just a working group. People often confuse the role of Apple in all of that because I don't know if it's a coincidence, but Apple released something that was a WebGPU prototype, which has nothing to do with WebGPU, the API that everybody agreed upon. And Apple created W3C group technically, but I can assure you it's just a collaboration between companies. Apple did not have a special role, but they contributed a lot to this. So once this Sketch API is shaping up, the thing going in the Rust ecosystem was very interesting because GFX REST transformed into something that's called GFX HAL, which is like a Vulkan-like API into multiple backends that we were really struggling to adopt wider in the ecosystem because it's so complicated. Vulkan is so complicated, and Rust API that Vulkan-like is also very complicated. So there was the Amethyst engine at the time, and there was some abstraction libraries, and it was going really, really hard. So at that point, I figured like there's a Sketch API that's portable. I might as well just implement it in Rust and give it to the ecosystem so that we can all be happy and have a sane API instead of the Vulkan madness that we were doing. So I started writing this as a personal project, and by 2019, it shaped up into something great. It was working well. Rust ecosystem was already started using it. I was able to merge it as an implementation into Gecko, which is the engine for Firefox. And at the same time, practically the same month, around the same week, Bevi announced the first version of the engine, and it used WGPU. So it was like a huge month for the project. And everybody realized that this is the way to go. And since then, we were trying to polish it. So the next year was done by throwing out SPRV Cross, which is the C++ shader translation used by MoltenVK, and implementing our own thing, which is called Naga. And Naga is currently shipping with WGPU everywhere. So this was successful. In 2021, the GFX HAL that was powering WGPU was thrown out and replaced by a from-the-ground rewrite, which is WGPU HAL, which I mentioned. It's much smaller. Doesn't have any baggage. better translation, faster. So that was a completely refreshed WGPU at the time. By 2021, it was pure Rust. It was pretty fast. And I asked about locking that question to Daryl because we had a lot of different types of storages. So you would have buffers, textures, texture views, and they would be locked separately. And we would support multi-threading, everything that like Google's implementation didn't even dream of at the time. But there was a chance that you would, in the implementation itself, you would lock them in the order that would deadlock, because this is open-threaded. So we developed a very sophisticated type-level mechanism in Rust to enforce the locking order, so that your code that you write is guaranteed to have no deadlocks for locking those assets. So that was one of the cool things. In 2022, I left Mozilla and stopped participating in the project. And fortunately, it was picked up by Connor Fitzgerald, who is a creator of Rend 3 and the rest of the community. So the project lives and prospers. And semi-recently, a year ago, they landed a big change in the architecture, which is called arcanization, which basically means that instead of locking those whole storages, like all textures, all buffers, they are now locking individual textures, individual buffers. That means less contention. Less contention on the locks, faster. The deadlock problem is still resolved the same way, but it's a much nicer implementation now than it used to be. So the library is still very well alive and prospering without my participation. Architecture-wise, there are three main things. The shader translation is done by Naga on the right. Then goes the API abstraction, which I mentioned, WGPU HAL. Again, it's a crate in Rust. Everybody can use it. It's not hidden from anybody. Targets all of the APIs. It's used by WGPU core. That's an internal crate which is not used by anybody directly. And it provides safety. It provides a sane API. But it's not necessarily an API for the end user. And there is a big difference. On top of it lives the API for the end users, which is like WGPU RS. That's what everybody is using. But Gecko would not use WGPU RS. It needs more direct access. So Gecko would use WGPU core and also native bindings to other languages. And it's surprising how many languages are using WGPU. It's practically, the list is like 10 different languages. Like everybody is using it from other places. The safety idea, we had a lot of discussion within the working group about how to provide safety and how to validate. And at some point, I remember Miles Maxfield from Apple, who also worked with me at Tesla recently. I think it was his idea that, like, why are we trying to optimize it if validating costs as much as ensuring correctness? So this is sort of like N equals NP kind of problem. If you have to validate and it takes you as much effort as actually provide safety, then why not just provide safety in the first place? So that's what WebGPU rolls with, and that's also a core idea for WGPU. Not just validating, but enforcing, ensuring rather. Synchronization one, so this is deeply technical. Every resource can have some combination of usages. Like those are on the left are different usages. For example, a copy is a usage. Binding to a shader is a usage. And some of those usages can work with each other, like they are shared. Some of them are exclusive, like copy destination is exclusive. You can't use it with anything together. So this is sort of like Rust mute versus non-mute kind of thing. In addition, there is ordering guarantees about how this is accessed. And when you record commands, what WGPU has to do is that for each resource that you use, and maybe it's a group of resources, you do something with it, like you bind it, and then within the pass that you have, be it a compute pass or a render pass, it would add the usage to the scope. So every resource gets accumulated like a set of usages within the scope, say within a compute pass. And then once this is done, WGPU can validate it. Oh, that set of usages is safe. You're good. Or it can fail. And this is also a place where WGPU can safely write it down into the native command encoder. And this is slightly a few caveats to this. Like we also did it directly by injecting the whole command buffers between the passes. Like we would record the dispatches, for example, and binds directly into the command buffer, knowing that they can be unsafe, and then create a separate command buffer that only did resource transitions, and then like schedule it in the execution right before our current command buffer. It's a little bit twisted logic, but it worked very well for us. Why are we using another shading language? That question has been debated to death, probably, especially like on Hackers News and Reddit. So I can't just skip it. There is many reasons for this. We had to develop our own because none of the existing shading languages were properly specified and designed for safety. SPRV is the only one that was specified, and it wasn't designed for either safety or even deterministic behavior in a lot of operations. So even if WebGPU took an existing language, it would have to basically fork it and cut it and add a bunch of stuff. So it would mutate it to a state where it wouldn't be anything like the original language anyway. So we decided we would just create our own. Another interesting point that, again, I think Apple pushed is that the success of the early web was because you could actually look at the page and edit it and run. So having like a text language that everybody understands is allowing this. And that's what we have. As for performance of like, oh, text parsing is slow or text parsing is error prone, Naga successfully shown that like it's extremely stable and it takes just 1.5 millisecond per shader, which is nothing because you don't compile shaders in isolation. You do it just because you need to create the pipelines. And pipeline creation can take a random amount of time from like 20 to 2 seconds based on how big your pipeline is. So shader translation is exactly nothing here. Naga has its own intermediate representation. If you write code for WGSL, which is the name of the language, WebGPU shading language, you can take intermediate representation from Naga and look at everything. Like here's are the constants that are declared. Here's the bindings. Like you can mutate it in place and push forward. So I encourage you to look at how this is organized. It's just like one Rust file, very clearly defined, lots of comments, very good code organization. I don't know who made this, but it's good. So in the end, I want to say that this should be the choice number one. It's the most robust and stable library today, the most supported one today. And it's pretty fast. Unless you have very specific needs, you probably don't worry about the host overhead. This is one of the pictures that's from Rust Avengers project. It's using like software ray tracing in a sense that it's done in shaders without hardware ray tracing. But you can do a lot of fun stuff with just compute. That concludes the WGPU part. Now we can talk about the next thing I did. So I decided to not pursue the WGPU because I wasn't happy with how verbose the binding declarations were. And also, the sheer fact that like most of the workflows are leaning towards just one giant draw call, or one compute draw call, or a bunch of compute draw calls, where rasterization and those ideas that your game should have 10,000 draw calls are a thing of the past. So I thought it would be good to have some API that was focusing on different things, that was focusing on ergonomics instead, and doing like less focus on rasterization in general. The other thing is that WGPU is doing is trying very hard, is doing everything it can to provide the driver with most correct information so that the driver can do an easy job at running your program. And this comes at a cost of host overhead and ergonomics, both. And I thought it's worth having a choice here. Maybe the driver can do its job without providing all the information we need. And when I say that, I mean like resource barriers and state transitions. Maybe the driver is fine. This is an example from Blade. It's using hardware ray tracing here. It's a scene editor where you can like drop things, rotate them, play with it, and you can already see that like even though the lighting is done by just an environment gray texture, the shadows are super soft and it looks very natural, just by the fact that it's like a ray trace scene. It was very fun to hack on this because of how API is structured. So yeah, the first principle, graphics should be fun. I don't know how much you guys program graphics, but it gets tedious very often. Like Rust Avengers had up to 15 different pipelines, and just declaring all the bindings to them is just so much churn that I couldn't bear anymore. So this is much easier to do. You don't need to do any bindings declaration whatsoever. The magic here is that your shader already has a lot of information, and your host has some information at the type level. So all you need is to just reflect some stuff from the host structures and then patch the shader. And I can patch the shader because of that magic that I was saying, that like intermediate representation in Naga is open. Anybody can use it. So I reflect it from the type system, and I just put the binding information into the shader itself. So the shaders become non-redundant, and the host side becomes non-redundant. This glue is entirely transparent. It's very easy to just add resources and iterate on this. The other thing is like uniform management is a pain that everybody goes through. There's no reason. It's just data, right? All you have is like your structure, and you want shaders to see that. Why not abstract this away? So Blade does that. Whenever you need some data, it's just a structure on the shader side, and you just set it, literally like push it on your encoder. There is no buffer management involved. And finally, safety is overstated. And it must be weird to hear from me because I worked on WebGPU a lot in my career, but there's a slide about this. But so Blade does not do any validation whatsoever. It relies on native tools like Vulkan Validator. It does copyable handles so that you can put them in hash maps. You can put them anywhere, and you can pass them to functions. This is validation story. So when we develop, it's super helpful. It's nice to be warned when something is wrong. It's nice to write correct code and be confident in this. Once this moment passes, that's basically it. You need to ship, and you need maximum performance. You don't care about validation anymore. So with WGPU, the unfortunate bit is that you can't easily flip this switch back once you develop like this. I think I mentioned that you can switch some shader stuff. So there might be some loophole to get there. But what I did with Blade is just like not worry about this at all. It's doing the complex things for you, like synchronization, and where you are not managing your resources correctly, you would rely on native tools like NVIDIA Nsight, like GPU crash tools from your vendors, whatever you have by hand. It's very lean and mean in a sense that like it doesn't respect your choice of tools. Whatever you want, you can use. So this is the example I mentioned. So on the shader side, the important bit is that we provide no binding information. This is just like a variable in the storage class. It doesn't have the bind group or the binding itself. And this is just data. Parameters is just a structure. And then the host side, we just give it the parameter structure directly. There is no buffer management. When we create the pipeline, we give it a type describing what kind of bindings there are, and it does the magic of writing and augmenting the shader with the bindings. The best part here is that despite all of that magic trickery, the shaders themselves, they're valid WGSL code, and Naga can validate them. So if you have a collection of shaders in Blade, you can have a test that validates their correctness, or run it as a part of your IDE. And it's not confused by the semantics that I'm doing here, which is a very good trade-off. In terms of synchronization, it's extremely dumb. It's like every pass is fully synchronized with anything else. Again, if you're using like 20 different render passes and 10,000 different draw calls, maybe that's going to be a problem for you. If you're doing AI and like a bunch of compute one after another, you probably don't care about this. So this works exactly fine. I haven't observed anything regarding overhead in anything that I've developed on this. Oops, sorry. This is an example of Blade in action. It's called Z browser. You might have heard of it. I integrated like Linux support and Blade as a backend for graphics because they didn't have anything for Linux. And this is how it's shipping today. It's using Blade. That's where the downloads are coming from mostly. Runs very fast, was very quick to implement. Like I spent practically a week just porting Z to Linux. Just 1 week of not even full time because I have a full-time job. So this was just fun. That's what my goal is, just make it fun. And I encourage you to try Z editor and see how quickly it responds. And it's running on Blade. Running on both Linux and Windows. And on macOS, I can also run it on Blade, but they're still hesitant to remove their old macOS backend. So that's a point of future discussion. Now, I mentioned the possible GPU overhead from Blade. This is because I'm not tracking resources at all. Like when I'm translating to Vulkan, I'm just telling Vulkan, all your resources use general layout, and the state just access whatever you need. So the theory was that it's going to make the driver produce slower code. I tested on 3 different platforms. 2 of them are different generations of AMD, which is like pre-Zen and, no, what's that? Yeah, pre-Zen, and so this is Vega and then Zen and then GeForce, and I didn't see any difference at all. This is Bunny Mark, which is like a bunch of sprites drawn. So it tests how much you can rasterize. You can hit the overhead of just recording commands in there, but with WGPU HAL, that's not the case because it's 0 translation overhead. So there is, on those platforms, there is exactly no reason to provide Vulkan with your information, at least with regards to rasterization. So the trade-off that Blade takes is paying off greatly on those things. If we go into like further details of like how bad this is. So one famous person on Kronos forums says that it's like state-of-art, weapons-grade laziness. That's us, yes. NVIDIA drivers from the start were advertising the fact that they don't care. So that's something. If you use NVIDIA, problem solved, like not even a concern. If you use AMD, it's more nuanced. There is, I think one of the biggest possible penalties is about the color compression when you rasterize, and that they have a lot of different checks for this, and I tried to dig through the code. I figured that probably before RDNA, it was potentially costly. But then again, my own test on Vega 8 GPU revealed that there is no cost. So I wasn't able to find anything clear. And on Intel, I didn't get to the end of it. In any case, if the rasterization is a problem, because we have the render process, we can change the layout. So even if that particular side is discovered to be a problem, we can fix it internally. That's not a big limitation. So again, conclusion, it's a library that's used in production by Z editor. It's very easy to use. I encourage you to look at the examples. It has like layers built upon it that are separate crates for asset management and ray traced rendering. of course, and the full like game-like package where you can instantiate a car and drive it. So it links to and physics and like Rapier and does all of the magic. This is an example of how it looks. There's nothing fancy, but it works and it's fun to program. And this is just the first demo I made with the project back in the day. So it's kind of sad that on the web those emoji don't show up. They do show up locally. Yes, so I'm sorry about that.
No,
yeah.
no, very cool.
Yeah.
All right, yeah. Any questions and commentary? Go ahead.
What would you say out of all of this, and I'm coming from actually a lot of this space, what would you say the highest integration of AI can serve or solve, or where would you meet this with AI? I think you had like one or two parts of the presentation, but I mean, we're at an AI talk, so what do you think?
You know this meme where Simpson sits in the bar surrounded by everybody? Like that's me. I don't do anything with AI, so it's hard to say. I believe AI means just compute jobs all the way, and probably like buffers where you don't have a problem of image layout transitions. So Blade would be a perfect fit in my mind for this.
I just want to kind of probe for your sentiment or thoughts around WebGPU. You know, this whole space always seems to go through like waves of redesigning and rethinking everything. And so I'm just curious, do you think like the WebGPU is sort of already hit the trash bin and waiting for the next redesign wave, or do you feel like it'll live out for quite a while as being the foundation for a lot of other systems on top?
I think it's going to live for a long time. I think it's a good future-proofing technology. It's already outdated, don't get me wrong, but at least it's outdated in non-critical ways that can be patched by extensions. The things that are not outdated are the threading model. The language is not going to be outdated, the shading language. So I think it's future-proof. The only problem I have with WebGPU approach is that it's trying to enforce safety at the wrong level. So it's a valid thing to do, but it's much easier to do it at a different level. For example, if you're writing like AI code, you have a bunch of operations on tensors, you probably know better when it's safe to like delete a buffer than WGPU. So it doesn't make a lot of sense to pay that cost for the abstraction in this case.
I'm also kind of curious about, you know, if you were to sort of be starting a large-scale cross-platform project, maybe let's say you're building a robotics platform, it has to do maybe a bunch of real-time transformation of cameras or buffers and processing, and in between those real-time operations, you potentially want to do memory-safe computation. Maybe you want to link the timing of those things. Just imagine sort of a decently complex system. And you also want to be sort of robust to the iterations of the hardware. And where do you feel like you would kind of start in building and designing that architecture? Would you start with like one particular GPU and then just try to kind of broaden your abstractions to meet them all, or would you really try to start from like a very shared point of view, or do you have a sense of like where you start from scratch, kind of
right.
What tools you might use? And obviously Blade might be one of those, but
I think I would just take Blade and remove all of the non-Vulkan backends from it, because the idea is it's very hackable, and then just add the features that I need. But otherwise, it provides a very sane base point for you to build upon.
cool.
Thank you.
Yeah, thank you so much. Thank you so much for joining us. Very intrigued by where this entire space will go.